I welcome you all to our seminar series, Energy and Finance. This year it's the first talk, and I'm very happy and glad that we have Florian Steinke today here with us. He is a professor in Darmstadt he's professor in Darmstadt, and he has a background in machine learning and optimization with application in energy systems and energy markets. And today he's presenting a talk on probabilistic electricity price forecasting. And as far as I know, most of the research he will present today is a joint work with Tim Janke, as you see him here already on the picture. So I'm very glad that he is here with us today, and the floor is yours. Thanks.
Okay, thank you very much for the introduction and for having me here. My group is called Energy Information Networks and Systems. I later come to what exactly that should mean. I want to present to you two works today, which are centered around the topic of probabilistic forecasting and with application to electricity price forecasting. And as Florian Ziel already said, it's joint work, or mostly the work of my PhD student, Tim Janke. Good, so let's begin. So price forecasting, what do I mean by that? So suppose we have the electricity day ahead market or so. So we have time series of the past, and then we want to predict the outcome for the next day. And we want to predict it probabilistically. That means we will not just predict one possible outcome, but we'll predict a distribution of possible outcomes, or a set of different outcomes where set and distribution, and if the set gets large enough, it's similar to a distribution. And the thing we want to predict is not just one value, but we want to predict kind of the whole trajectory. That means, in some sense, a vector in a 24-dimensional space. Why do we want to do that? That's actually an interesting discussion, and we are just recently doing some work on what is the value of a good forecast. So mostly they're used in economic dispatch, in stochastic with stochastic two-stage stochastic optimization approaches. If you want to determine bidding curves for power plants, storages, consumers, whatsoever. Or, I mean, maybe you're familiar with this 6-hour rule. So if the electricity price is 6 hours negative in a row, then you don't get refunded as a renewable producer. So that means it's very important for you to predict these events and not to waste your energy. For this economic dispatch, we typically solve it via sampling scenarios from the uncertainty distribution, which are called, the samples then are called typically scenarios. We don't exactly need the distribution in kind of formal description most of the time. That will become important later. Okay, so what are good properties, or what are properties of a good forecast? So not all possible vectors in 24 dimensions are plausible price time series. So certainly we have a certain range of prices that are plausible. We also have the property that consecutive hours typically don't have kind of completely independent prices, but they have some connection because the underlying reason is maybe a strong wind area moving over Germany, which has, of course, an influence on the prices. We also have that the uncertainty should be probably different, whether we are talking about peak prices or whether rather low prices. We also have some asymmetry typically, that if you would do a mean prediction, then probably the deviations to the lower part are at least sometimes lower than the deviations towards peak prices. Yeah, so these are important properties, and these properties, I mean, okay, dependence between different time steps you can cover by a classical Gaussian model. So we could predict some multivariate Gaussian distribution. If you want to have the dependence dependent on the price level, or if you want to have asymmetry, then you cannot cover this with a Gaussian distribution, or only approximate it with a Gaussian distribution. So in the first part of the talk, I want to ask, can we do better than predicting Gaussian distributions? And obviously, the answer will be yes, we can. And to understand how and why, let me go a bit into the machine learning area. And I mean, machine learning is a pretty wide field, but lots of the original research and even today is centered around images. So let's talk about images. And let's talk about the most classic data set there is. MNIST is a collection of handwritten digits, and the typical machine learning task is to discover kind of which letter is it. Let's look at it formally. So these are 28 by 28 pixel images. If you put all the pixels as values below each other, then it's a vector in 784 dimensions. So here on the left-hand side, I've drawn 6 training examples of these vectors or images. Let's try to do a model of it. I mean, maybe the easiest model is to say, okay, let's sample just uniformly vectors in 784 dimensions, and let's keep it to the interval 0, 1. Then you would get vectors which correspond to images like these ones which are shown here. So these are images, but it's not images of real handwritten digits. So we already understand that not all vectors are digits, and we have to figure out, so in this high dimensional space, there is kind of the real images cover some certain area. We can describe that by some probability distribution. Let's try to understand that probability or model that probability distribution in a more detail. So the next best thing one could do is, okay, let's classically do principal component analysis, or let's just assume it's a Gaussian model. So we could just compute the empirical mean, and then we could estimate the variances around it. And again, I could use this model of a distribution and take samples from it. So I generate samples of this multivariate Gaussian distribution, which I've estimated from the training examples. And the results, what I get is what you see here on the right-hand side. So it looks a bit more realistic than the uniform distribution, but still it's not realistic numbers. Good. So what does it mean? That means that the space or the set of all handwritten digit images is not a Gaussian distribution in this 784 dimensional space. And I would even claim it's not in any other classically known family of distributions. So what can we do if we don't want to use a parametric model of a distribution? So if we were in one dimension, the classic approach would be maybe to use quantile regression. So we could determine different quantiles, and that would describe us a distribution without making an assumption about the kind of total form of the distribution. However, here we don't want to predict a one-dimensional distribution, but we want to predict a distribution in 784 dimensions. So unfortunately, this approach doesn't work as well, because here really a quantile would be something like a hypersurface and be very complex. So what can we do? We can do generative models. I'll explain in a second how we can do this for images, but let's understand first that this is a very classic approach, actually. So if you consider how would your computer generate a normally distributed random variable. So the way it would proceed typically is it would first generate a uniformly distributed random variable. So by multiplying numbers and taking certain subsets of these numbers, you can, with some confidence, say that the result will be uniformly distributed in 0, 1. And then you apply a known function with parameters mean and variance or standard deviation. You apply this to this function, to this value z, and you get a new x, and then you can be sure that it's actually normally distributed. And I guess most of you are aware, so this function is exactly the inverse cumulative density function, because that would map a uniformly distributed variable into one of your desired distribution. So this is the one-dimensional case. But now we want to generate images or price time series which are in a much higher dimensional space. So how can we go about it? We could actually just copy this idea. So we also take some noise source or some random variable, some simple random variable. So maybe we don't take one, but we take several of them, let's say n. We feed it into a deterministic function. And then we hope that the output is in the distribution that we want. And of course, the distribution that we can obtain here for x depends on the function. So let's make this function have some parameters or weights. And by adapting these weights, we can change the probability distribution that we're actually modeling. And then we just adapt it until it models whatever we want to model. And today, of course, we have lots of tools and many reasons to believe that deep neural networks are a function class which is able to model many functions. So why not take a deep neural network? So then we would obtain a model of a probability distribution. It would be a model where we, in the end, can generate samples. That's why it's called a generative model. But note that it's typically, we don't know the density or CDF or anything of the output. So that would be actually very complex because this function is typically not an invertible. So yeah. But the claim is we can still do a lot of useful things even if we don't have a density. So for example, we can compute expectations by just basically sampling examples and then taking the empirical mean. And this is an unbiased estimator. If you do it long enough, you will get a more and more precise estimate. We can compute conditional distributions by just filtering our generated samples. We can compute histograms, which would give us a way to approximate probability densities if we wanted. So all of this is very similar to Monte Carlo approaches where we, in the end, do very similar things. And I will to some part show, and maybe you already know that with these sampling or generative models, we can basically perform all the operations that we need to do learning or to actually do forecasting and so on and so forth. So whether that's efficient or not depends a bit on the use case you want to cover with it. And also this generative model is universal because for any distribution you can, and for any random space, you can find at least one generator function. Proof is pretty obvious because if you look at classic measure theory and the definition or the mathematical definition of random variables, that's exactly what you're doing. So you have some random space and you have a map into your value space. So the only condition we have to make is that this set of functions is probably pretty large. So we need some model which can model a lot of things, and that's again is the reason why we might want to take maybe neural networks. Okay, so now the question is, how do we train such a probability model? So how do we adjust the weights so that the distribution of the axis is similar to our training data? And here I want to present one idea, the so-called generative adversarial networks idea, which is very, very popular in machine learning for a while now already, and still is. So what is the idea? So we have our generator where we can generate examples X. So let's say images or price time series. And now we need to measure how good are they. And generative adversarial networks, they have a second function or neural network, which is a classification network. So you take an image and you try to predict, is it either a generated image, so a fake image, or you can infeed your true training data, which are called here Y. And then, of course, you would want to predict that it's actually not a fake. So the idea is the generator network does a good job if the discriminator cannot tell anymore whether it's a fake image or not. So if these are very similar, then obviously or intuitively your generator must be good. So how can we use that for training? So for example, we could first say, let's just take any generator or just take initial values for the parameters here. So we generate some random generated images. And then we train a discriminator to separate the true images and the generated one. So if you think back to these uniformly distributed 0-1 pixel images, then it's a very easy task to train a discriminator which would discriminate between the two. So once we've trained such a discriminator, let's say a logistic regression type thing, then we can determine the probability for each input. What is the probability of it being fake? And then again, we can train the generator to decrease the probability that the discriminator thinks it's a fake, right? And so the generator tries to get better at producing things that look like real images. And then you train the discriminator again and back and forth until hopefully it converges in some direction. So we come later to the discussion. This process, of course, is non-convex and not necessarily super stable. But still, it's a nice idea that sometimes does work. And we can later discuss whether there's maybe also other approaches which are more stable. Okay, so this has actually worked very, very well in image processing, so in machine learning. So here is the original 2014 paper. So here, for example, you can see MNIST generated digits, and on the left, on the right, the yellow marked ones are always the closest examples from the training set. So you can see, I mean, easy would be if you just memorize all the training set. If your network is large enough, it could do that. So if you look here precisely, I mean, they are similar, but they're not exactly the same. Actually, so here the thickness of the lines, for example, is different, and the way they are different is somewhat plausible. But still, I mean, the early successes were maybe rather minor successes, where you can see some images, yes, but today, actually, the images you can generate, they look more or less perfect. So here, these images on the right are generated images. So these are people and persons that don't exist, or animals and beach scenes that don't exist. Yeah, generated by such a model. So you see, I mean, this is a big reason to believe that this adversarial training of generative models can be super, super powerful. And that was our motivation to see, can we not do something similar also for electricity price forecasting if we there also want to predict multivariate distributions. Okay, however, there are some differences between modeling images and electricity prices. So first of all, when we model electricity prices, we're typically not interested in an unconditional distribution of how do typical electricity prices look like, but we are more interested in a conditional distribution. So given a demand for or weather forecast, maybe what is the likely price development of tomorrow? Also, our output is high dimensional, but it's not millions of dimensions. So if you predict one day, maybe it's 24 dimensions. If you predict a week, then maybe it's a bit more, but yeah, it's lower. But also our training data is much lower. So these image things are trained with billions of images. Our energy market data, if we go back maybe the last 3-4 years or so, then it is a reasonable amount of data, but it's not infinite, or it's not 10 to the 9 examples. And also, if we do things for energy trading or so, then uncertainty is quantitatively important. So we have to be sure that we not just predict somehow uncertainty, which often actually in images, you just have to show that you can somehow generate a variability and differences. But there is not a clear quantitative measure. But if you want to really do trading, then in the end, the quality somehow translates into euros that you earn or don't earn. So we also have to care about that. So, and based on these 3 points, the first work which I want to introduce is a paper at the PMAPS conference, so probabilistic methods applied to power systems, where we address exactly these 3 issues when we apply generative models to probabilistic electricity price forecasting. So first of all, we do conditional forecasting. So, and as input here, we don't take a weather forecast, but instead we take deterministic forecasts. So an ensemble of deterministic forecasts. So that seems a very plausible approach, since many energy companies already have systems for deterministic forecasting and they trust these systems. There's also often a degree of prior knowledge in these systems, and we want to keep that. We, for the point high dimensional and few training data, we address this by using generator functions which are not arbitrarily deep neural networks, but rather simple generator functions. And also by introducing some inductive bias, as you'll see, that makes sense for the application. And for the last point, we want to train our models. So we adjust the parameters of a generative model, not as generative adversarial networks, but we want to minimize a criterion that has some guarantees. So what could such a criterion be? And this will lead us to the scoring rule discussion. So I'm not sure how familiar all of you are with it, so I will briefly review it. So now we want to make predictions. So we generate a predictive distribution Q of some quantity Y, which depends on some condition Z. And the problem now is that for each such generated predictive distribution, we only get one sample. So I mean, today I will make a predictive distribution for the electricity price time series tomorrow. And then tomorrow something will happen. One price time series will be realized. And now the question is, was my prediction correct or rather a bad prediction? And the problem to solve here is, so if my red thing is the predicted distribution and X is the true outcome, so what could that mean about the true distribution? So with a high probability, the sample X is somewhere from the true distribution where the true distribution is actually very likely or has a high probability mass. So then can you actually see my mouse? Can you give me a short note? Yes, you can see the mouse. Okay, good. So if with high probability, probably the true distribution is somewhere where your sample is. So that would mean that my prediction was rather bad. On the other hand, it could also be that, I mean, since we make a probabilistic distribution, it could also be that it's just an unlikely event that happened. So maybe the true distribution is actually quite close to my red predicted distribution. It was bad luck, so it was an unlikely day. So how can we distinguish between the two? And that's the idea of using scoring rules. And the answer, I mean, qualitatively is, for one example, you cannot decide which one is the case, but if you have repeated experiments, then you can. So what exactly is a scoring rule? So a scoring rule takes a predicted distribution Q and some realized sample and produces a score. And a score is just a real number. And if you now repeat this experiment, you compute several scores. So you take the expectation over your true data generating distribution P, then it will boil down to also a distance between our predicted distribution and the true distribution. So now we can say a scoring rule is proper or strictly proper if it is maximized if the forecast is true. And whenever the forecast is wrong, you get a lower score. So that seems like a sensible definition. So the question then becomes, is there a scoring function which actually has this property that it's strictly proper? And yes, there are. So if the density of your prediction is actually known, then, for example, the log density is a scoring function, and maximizing the score then is the same as doing maximum likelihood estimation. However, we want to look at generative models where we don't have a density. So we have to do something which we can compute based on samples. And there is actually, in the univariate case, a so-called continuous rank probability score, which you can, so again, it's a map from a distribution and a sample. You can write it as this integral, or you can write it more in a sample style. So we have the expectation of the predicted y minus the truest sample minus the kind of variance or the variation between prediction samples. And you can show also that this is a strictly proper scoring rule. So this only works if you have a CDF, a one-dimensional CDF. So how can we generalize it? And actually straightforward, I mean, it's maybe not straightforward to prove it, but here if you look at the formulas, it's straightforward to just replace in this expectation representation, replace everything by vectors. And then again, you can prove that this so-called energy score is a strictly proper scoring rule if the beta is between or in between 0 and 2. And in case you're familiar with the maximum mean discrepancy framework, which is related to a two-sample test, so are two distributions the same or not, has been familiar or popular in the kernel methods branch of machine learning, then actually it's also a special case of the maximum mean discrepancy. Okay, so this thing here, I mean, if you replace the exact representation by the empirical mean, then we can, based on samples, compute a quantity which is not exactly the energy score, but which is an unbiased estimator of it. And that is something then we can optimize. So this is the idea we are proposing here. Good. looking again at the electricity price and everything together. So let's assume here we have 3 time steps, 1, 2, 3. Let's assume here in this case we have 3 deterministic forecasts, which are not exactly the same. So we will we can take the mean prediction, of course, for each time step. We take the mean of the 3 predictions, which will be the black line. So this is a vector which we put into our generative network. And we also put some noise into this. And here we assume that we have 1 noise dimension per time step, and that the higher the variance or the variation range per time step is, the larger we make this 1-dimensional noise factor. So this is a useful inductive bias, because if we then would take a rather simple function, for example, which would map always, basically do an identity map, so mean plus this thing, then we would already get something that's relatively reasonable. And then we give the network the chance to improve on that. However, we want to keep the whole training relatively robust and not with too many local minima. So that's why we take a rather simple generator function. So in this case, only a linear function. And when we have that, then of course we can draw more samples, and we can actually generate as many samples or scenarios as we want. And then we have our generative model. And to fit everything, we minimize the energy score of our predictions. So this idea actually works quite well. So I mean, first of all, the example trajectories which we obtain, and they look plausible. So they have a dependence between time steps, which is plausible. They have kind of asymmetric variances, what we wanted to obtain, which are also kind of plausible in where they are. With the probabilistic forecast, we have other measures to look at it. So for example, it should also be balanced. So the true values should fall into the predicted quantiles. That's not perfect here, but still it's relatively okay. And then we can look at these statistical performance measures, either the energy score or the CRPS, if we look at the marginal distributions. And we can see that our what does it say? Implicit generative electricity price forecasting actually has the best score. And for example, doing, I mean, you could do a Gaussian estimation performs worse. Or if you want to get away from the Gaussian, you could also use quanti-regression to estimate the univariate marginals, and then do a copular model, a Gaussian copula, to model the dependencies. This would allow us to get better than the Gaussian distribution, but still it performs in these numbers at least worse than the direct approach of training a generative model. And since we've kept the generative model relatively small, the training here is relatively efficient. And it's not like often, sometimes in neural networks, it can become really difficult to make everything converge, but here actually it's pretty robust. Okay, so much for the first work. Now I want to switch a bit the approach. We'll look at a similar problem, but from a different perspective. Yeah, let's again say we want to model a multivariate distribution. We have some x's given, which are following some distribution. For example, here, I mean, just for the example, we took a mixture of Gaussian distribution. So we could, of course, directly now what we discussed before basically was to have a generative model which directly approximates this distribution, which you can do. But maybe sometimes it's also useful to do something else. And for example, we could take the one-dimensional or the cumulative density function of the marginal distributions and map our data into this unit space. So now basically here each value is mapped to its quantile value, which would give us a different distribution. Now it's all between 0 and 1 in all dimensions, and all the marginals are uniform. And of course, this, because the CDF is invertible, at least if we have a density, then we can go back and forth, and this is just an equivalent representation. So why might that be useful to make that step? So this step is basically the key idea behind copular modeling, and it allows us to decouple the modeling of the univariate marginal distributions and the joint dependency structure. So I want to claim roughly that modeling univariate marginal distributions is relatively easy. So we have lots of known distributions which you can use. You can use histograms, you can use quantile regression. And often in some applications, you also have some prior knowledge which actually dictates you kind of the shape of possible distributions that's possible for a single value. If we go to modeling the joint distribution, so this copular distribution, how it's sometimes called in the unit space, if it's high dimensional, then again, you can do Gaussian copulars, which is a parametric assumption, which in many cases might be too rigid. For example, this case could not be explained. There's other constructions which you can use. You can split it up into two-dimensional copulars and make trees of two-dimensional copulars, which is so-called wine schemes. That's relatively flexible, and you can get good qualities for many things, but it's also, you have to build a tree and optimize over trees, so it becomes a bit kind of discrete optimization and not so nice. So idea again, why not use generative models? Can we train generative models to obtain a copular? And that's part of our paper at NeurIPS in last year. So how can we do a generative model to model a copular? So, I mean, straightforward would be we just model, or we take a noise space, we map it through our neural network, we obtain some output, and then we, make it similar to the copular distribution. Now we would have to ensure that actually the output is always between 0 and 1. So the classic neural network approach would be to put a sigmoid function in the last layer, which would ensure that your output exactly has this property. However, since we know that here the marginal is uniform and we have this mapping function, then we would also know that the marginal we have to have at the stage before this sigmoid function actually has to have a very strange distribution. So now our generator model here would have to train to obtain these marginal distributions. That's also maybe not so nice. So why not take a different function to map from here the unit space to our output space of our neural network, which is generally something like R to the N. So for example, we could take the empirical CDF of our generative model here and use that to go back and forth here. And that would be a nice property here would be, I mean, first of all, it guarantees that we're between 0 and 1 here with our prediction. And it would also guarantee that basically we could have any marginal in our green space, so in our latent space. And by using the CDF here, the univariate CDF, we would again guarantee that the output is really marginally uniformly distributed. So that it's actually a valid copular distribution. Good. So this is the key idea. We want to train this setup. Again, now the question is, how can we get this univariate CDF? And the idea is we just basically do a counting argument. So we take a batch sample or a set of samples, and then we have the empirical CDF here, summing up them in a sorted order. Of course, if we want to train this, then having a non-differentiable function here is not so nice. So let's smooth it out. with a softmax. So at least for training, we can do that. Once we have completed the training for actually making predictions, we can then again go back to the true CDF. And then we can also take a very large sample so that the CDF approximation actually will be very high quality. Good. And in the end, as before, we'll train the two distributions to minimize the energy distance based on a sample-based estimate of the true distance. Good. So if you look in the, I don't want to here show all the results. I mean, it's many numbers and images, and you can assume that probably our approach has the best numbers. So if you look in the paper, we looked at synthetic data. We did some real data examples with exchange rates. We also did some image data. What we have not done so far is energy data, or we've done it in private, but we have not published it yet. So this is mostly due since at NeurIPS it's easier to publish stuff which is about images than about energy. But we are very confident that the same approach will also be working for energy data. Okay, so let me sum up and hope then we're roughly in time. So generative models are a very powerful tool that allows us to leave the world of multivariate Gaussian forecasting. They can be used for many different purposes. And coming back to why do we need a multivariate forecast in the first place? Mostly we want to do some form of stochastic programming. And in most cases, we'll do that with the sample average approximation. So we will use our distribution to generate samples in the end. So then maybe it's not a big mistake if we don't predict a continuous distribution first and make samples afterwards, but if we just have a model which directly generates samples. Interesting question is, when exactly do you need a multivariate forecast? Yes or no? Maybe we can discuss about that later offline. And the nice thing about using neural networks in this framework, of course, is that it allows us to use a lot of the tools that are out there, TensorFlow and the like, which helps us a lot to implement these things relatively efficiently and with few coding effort. Okay, so much for the topics. Just 1 minute on what are energy information networks and systems. So it's a topic that has been invented in Darmstadt to connect a bit the classic energy engineering, power engineering group within the electrical engineering and more the computer science fraction or people in there. So I decided that energy information networks and systems means we're looking at energy management, so from different perspectives. So we look at algorithms for economic dispatch and also for dispatch which is limited by technical things. So we have other works which focus a lot on resilience and whether frequencies and voltages can be kept in certain ranges. Once you do, of course, economic dispatch, you can also ask the question, what would be the best system to actually do economic dispatch? What either kind of from a more macroeconomic view. So if you're the Mr. Habeck, so what would be the best way to do energy transition, or more from a local perspective, microeconomic? If I have a company or university, what should I do now? And we also try to do some things in automation systems, so to make it easier to actually get these algorithms in the field. And to this end, we mix a lot of technologies. I mean, we discussed before, so I'm originally coming from physics, moved through computer science, now to electrical engineering. You're in economics, so I think a lot of tools are kind of computational tools which are used in many different disciplines. So we're working on modeling, optimization, stochastic things, forecasting, machine learning, however you want to call it. So thank you very much for your attention. I'm hoping for some interesting questions. And of course, I would very much welcome to stay in contact with you. So I think many of the topics you're working on are very interesting to us. And I hope we can, in some way or another, also collaborate in the future.
So yes, thanks a lot also for the nice words in the end. And I'm pretty sure that we will have questions. Yeah. So I have a couple of them, technical ones and more general ones, of course. But if they are first questions from the audience, then I would prefer them. So you could either raise your hand and yeah, then you can tell your question directly, or you can use the chat to just write your question in. I think we are not too many people, so we can keep it this way with questions. So yes. Yeah, and I don't, and of course, no, people still need some time if they want to write. If not, I would start with one question, which is very close, a general one, and close related to one question you mentioned at the end. What is basically the value of multivariate forecasting? Why we need this? You also mentioned at the very beginning that it's still more or less open. Of course, from the theoretical point of view, it's more information. It should be more valuable, and it should be better to have these kind of predictions where you have the dependency structure correctly described and so on. But do you know anything behind, say, this theoretical statement that supports the theoretical idea of going in this direction more and more?
Yeah, we're just doing some work which is under way of being published. So if you have a economic dispatch problem where you have the physical system couples multiple time steps. So you have a storage, or you have a power plant which has startup costs or so. But you're only allowed to bid on single time steps. Then it makes sense to have a multivariate prediction, which is a common case. So if you want to predict, so for each time step, you want to have a bidding curve. So for which price you would buy how much. If you want to determine that in a optimal in expectation way, then you should use a multivariate prediction. And actually the quality of the multivariate prediction is important. The question practically, of course, is by doing a stochastic. So if your forecast is perfect, then you will have a benefit. If your perfect forecast is not perfect, which will always be the case, then the question is there still a benefit? And that's something we're also working on at the moment to quantify that experimentally.
Okay. Yeah, so due to the high uncertainty risk, especially in the copulars and so on, yeah, the question if it's worth taking such a relatively complex structure like the GANs, implicit copulars and so on to benefit from this. Yeah. Okay. Do we have some other questions so far?
I mean, for the copular thing, it first sounds very, very complex. But in the end, I think actually it's pretty natural, and it's actually good for trust. Because since you can control the marginal distributions individually, I mean, that already gives you a lot of trust that you are in this plausible range, and that you're maybe for this one time step, it's plausible, right? And then if you have additionally some benefit of getting the correlation between time steps correct, there the intuition of us humans is probably not very good. And then you can show there that it actually numerically helps, then maybe people will accept it.
Okay. So we have one question.
Hi, this is Christoph Weber speaking here. Thanks for that very nice talk. And a bit following on what Florian just asked, I was wondering what we see in both price and load data and other, not in renewable data, but everything that is human, that are patterns related, for example, to day of the week or to holidays. And yeah, 20 years ago, again, when a colleague of mine worked on load forecasting, the practitioner said, oh, well, we are quite good in load forecasting, except when it comes to the period between Christmas and New Year. So now we have much more powerful tools. But the assumption of similar marginal distributions in that special period than in the rest of the year, I feel, yeah, you can use that assumption, but it's an assumption which I believe is quite strong and might be misleading. Any ideas on how you will approach forecasts in such special days, or even Christmas is difficult because the weekdays are changing every year, but there are also other special days like All Saints, 1st of November, which is not a public holiday in all parts of Germany.
Okay. Yeah, I mean, obviously you can also make your prediction dependent on kind of an indicator of whether it's a special day. And if you have sufficiently much data, you can also make it dependent on whether it's Christmas or not. I mean, technically you can do that. The question is, do you have sufficient training data to really make a reasonable forecast? I mean, I can understand the practitioners that they maybe say, well, maybe we don't have enough data to even make a real forecast, and we should better use our common knowledge to whatever, get a range of what is possible. I mean, there maybe the copular approach could be very useful, because it would allow us, or would allow you to exactly encode this knowledge, at least for the marginal distribution, by maybe not using a learned marginal distribution, but you could say, okay, I believe this range is possible, so write it down as a uniform distribution between this and that value. Right, so it would allow us to bring in some of this prior knowledge. I mean, obviously, if there is very little data to validate it, then it's hard to say whether it's actually better or not better.
Thank you. Yeah, perhaps, if I may, I would ask a more general question, but related in the fact when you are talking about energy system design, we are in a similar situation. If we think 30 years ahead, well, we have basically, and we want to design a system that works on an annual basis, and we look back, we have perhaps data for the last 30 years. So there's a very limited amount of data, and moreover, what econometricians call a structural change is more than likely to have happened more than once over the last 30 years. But 30 years back, that was we had not even competitive electricity markets in Germany.
Yeah, I fully agree with you. I mean, one thing is if we look at least from the macroeconomic view, so what is the best way for Germany, then fortunately the market regulation is not so important, because I mean, if everything efficient, then hopefully it gets the best solution. If it's efficient, so maybe that's not always the case, but of course, if you would try to run an energy system design model from 2000 to 2020 and see whether it would make the right prediction, and you would ignore what happened really, then I guess you would not have predicted Fukushima and that we end nuclear and so on and so forth. So, and I guess in the future it will be the same. So for this energy system design models, actually, I would not assume that they make predictions. They generate scenarios what could happen, which are in itself consistent. They give you a guideline of what would be a reasonable way under current knowledge. But then, of course, it will happen differently. What is an interesting question actually there, and then maybe you're working on similar things, is, I mean, really important is only what you have to decide today, right? So if I make a path from now to 2050, so who knows what happens in 2040, and actually I don't care what happens in 2040. So I just want to know that I make the right decisions today. So in many of these models, it's not examined yet how the uncertainty increases, of course, over time, and how the value is of making decisions later, or being able to make decisions later and to change the path if something happens. In principle, you could do it with multi-stage programming or so, but I guess it's not done, or not extensively at least.
I would say not extensively. I did some small works in that direction.
Okay, cool. That would be very interesting.
15 years ago.
Okay. Could you send me a reference?
Yeah.
I would be very interested to look into that.
But it was not that formally mathematically, but I think, yeah, more guided by a combination of intuition and some knowledge of stochastic programming and time series modeling.
Yep, cool.
Okay, so thanks for this question and questions. We have another one from the audience.
Hello, good evening. Michael Vogelsang from the Hochschule Ruhr-West in Mülheim, just next to Duisburg. Thank you for the invitation and the very interesting presentation. My question is about the generator function. If you have an external shock, I would be interested to have your opinion about the behavior of the generator function. Is it stable? Is it more resilient than, for example, if you have a regression function? So if you run a regression and then a shock like COVID lockdown occurs, you can try to work with a dummy, and with a lot of luck, you can go on to run your model, and how you can the generator function reacts here. Thank you.
Difficult question. So, I mean, let's say you take the simplest possible generator function would be just a linear function. And if you have your shock variable is somehow one of your inputs, whatever exactly is, you were somehow a very strange person that included the number of COVID or ill persons in your electricity price prediction, because it has an influence on the demand. I don't know, probably nobody did before COVID. Then, I mean, you would know how it would react, right? So I mean, you have your linear prediction thing, so you can analyze what will happen. Whether it's actually a good prediction, I would strongly doubt it, because it's yeah, the impact has not been seen before, so it's, I mean, you're training this data on data, this model on data that you've seen, and not on data that you have not seen.
Yeah, but if you have a shock in energy prices, a sudden shock, yeah, which could be the result of a lockdown, for example.
Yeah. I mean, what you of course can do,
and then more resilient than maybe regression coefficient, if you.
I don't think so. But I mean, as for regression, we also train these models always on the latest data and weight the latest data higher than the older data. So, I mean, at least after some time of the shock, your model would adapt to it. But in the transition period, of course, it probably would be wrong.
Okay, thanks.
So thanks. Do we have a further, maybe last question from the audience? If I don't know. But, okay. So I mentioned I have a couple of them, but they are more technical, and I would proceed this or postpone this to a private discussion, say. If this is not the case that we have further questions, then I would thank the speaker again, Florian Steinke again for the presentation. We are just in time, and thanks for the audience for the questions, and especially thanks for participating here in this energy and finance seminar. Yeah, it's great that we had all you here, and we hope that in the next terms you will have again a similar series of interesting talks. Okay, so
thank you as well.